We've now seen an example of how we can take a classical problem, basically the particle in a ring, and translate it to quantum mechanics and get wave function solutions for the quantum mechanics. And it involves something no more complicated, at least in that particular case, than the classical wave equation. What I want to do now is begin to talk about the quantum operator versions of this quantity, this angular momentum, and do it in a way that we can use these in a very productive fashion. Now, I'll remind you that the angular momentum is a vector quantity, so I'm going to look at the vector definition for it. So we're talking about now rotation in three-dimensional space is simply that L is equal to the position of the particle with a cross product with its momentum. So label this as cross product. Now, how do we define this? Well, I want to write this in a vector fashion. So I'm going to write L as equal to a column vector, which has three components, x, y, and z. And these are going to undergo a cross product with a momentum vector that also has three components, px, py, and pz. So how would we go about evaluating this cross product? Well, I'll outline sort of the formula for it. We would take if I want the initial row here, I'll take the component in the second row down here times the third component down there, and then subtract the second one over here with the third one over there. So in other words, I would take 2 times 3, and this is in the first vector and the second vector, minus 2 times 3, where I reverse those. So in other words, I'm going to take y times pz, and maybe I should write this over here, y times pz minus z times py. I'm simply taking this quantity times this minus this quantity times this. Okay. Now for the middle one, I would take 3 times 1 minus 1 times 3 for those. So I would take z times px minus x times pz. And finally, for the third one, I would take 1 times 2 minus 2 times 1. So I would have x py minus y px. All right, now I'll note that this gives us basically numbers because we're talking about a classical definition for for the angular momentum. But I want you to note a couple of things about this. One, there's a cyclic permutation. So I start with y and z here, y pz. I then move to z px, then I move to x py. So I'm moving cyclically between x, y, and z in a cyclical fashion. And the same is going to be true over here. All right, what this produces now is an Lx component, an Ly component, and an Lz component. So the vector that I'm making out of this would be this vector out of this cross product between these two vectors. So you can see that the cross product, the effect of it, is to produce a vector itself. Now, a geometric interpretation of this would be as follows. Let's suppose that I have a sheet here, and I'm undergoing rotation in a counterclockwise direction on this sheet. The angular momentum would be a vector that points perpendicularly out of that sheet. And this is something called the right-hand rule. Because you could imagine if you were following the trajectory of this rotating particle with your fingers or your right hand, then your thumb would stick upward along the L direction. So this is the sense in which this cross product takes place. All right, so now we have definitions for these things classically. How would we convert this to quantum mechanics? Well, in fact, in quantum mechanics, we're simply going to take all of these classical entities and convert them to their quantum operators. So in other words, I would write down something like this. I would have Lx now as an operator, Ly as an operator, Lz as an operator. And these things would be defined directly as y operator pz operator minus z operator py operator, and then I'll have similar things to what's written over there below this. So, and LZ is xpy minus ypx. All right, so now we can express these components of the angular momentum in terms of actual quantum operators. Now, we could take this a step further and remember that in the alpha coordinate, we would have that the p alpha would be minus I h bar, the derivative with respect to alpha. So if I make that equivalence here, I can actually write these components of the angular momentum as follows. I'll have minus I h bar times y d dz minus z d dy. And for the middle one, I'll have minus I h bar z d dy, ddx minus x d dz. And for the third component, I'll have I h bar x d dy minus y d dx. So now we actually have written down, what amounts to a prescription for how we would evaluate these things when we use the angular momentum operator in a real system. All right, now I'll finally note that we can develop all sorts of interesting relations between these angular momentum operators if we take into account the fact that in any given coordinate, for example, x and px do not commute. They equal I h bar, and this would also be true of y and py, and also true of z and pz. So we can use this fundamental relationship, this fundamental commutator here, to now develop expressions for commutators like Lx, Ly, for example. All right, and that's something that we'll do a little bit later on in the lesson. In fact, you're invited to do it in a practice problem that's part of lesson, I believe, 3A. All right, I want to finish with a review of since we're talking about commutators, some helpful rules about commutators, especially when we have products of commutators or products of operators appearing in the commutator. So for example, we may be faced with evaluating this sort of commutator. How would we do that? Well, we could write this out as AB times C minus C times AB. All right, but we can also simplify this a little bit by adding and subtracting the same term in the middle. So for example, what if I wrote this as AB times C and then subtracted A times CB? All right, if I subtract that, I need to add it back so that I haven't altered the value of this commutator, and then I would subtract the term that's left, minus C times AB. All right, but now when I look at what I've got here, okay, I want to combine these two terms together, and I want to combine these two terms together. Well, if I combine these two, I can write this as A times BC minus CB. Now notice it's important. I kept the A in front. It's the first operator in both of these sequences. Similarly, over here, I've got B as the last operator in both of these sequences, so I might have AC minus CA, and then followed by the operation B. Okay, now you should recognize that this is simply the commutator BC, and this is simply the commutator AC. So at the end of the day, what I have is the operator identity, that if I have a product of operators in a commutator with C, that is simply going to be the A operator times B C commutator plus the A C commutator followed by the B operator. Okay, and this is a general rule that you can use whenever you're evaluating commutators like this. I should note that you can also show this related commutator, that this is equal to B times the commutator of A and C plus the commutator of A with B followed by C. So this is also true.